are some properties that you can, I don't know. These are properties that sometimes we feel look like common sense, okay? But it's still something we need to officially define. If we have addition inside of our integral, we can split it into two separate integrals by adding them together. If we have subtraction inside of our integral, we can separate it into two integrals and just subtract the two. Okay? If we have a constant multiplied to our function inside the antiderivative, it is the same as if it's multiplied to the outside of it. So you can use these to help you. Some of you may not use them at all. We'll probably use them more next semester when we really get into Unit 4. Okay, this is more just kind of like an introductory to it, so we can hit the ground running after break. But we have these if we need them. Okay. On Friday, we talked about these next three concepts. Don't write them down because you already have. Okay. We talked about how the antiderivative of 0 is c. Okay. We talked about how the antiderivative of k is kx plus c. And then we talked about the power rule. Now, what we didn't do a whole lot of on Friday, we did a little bit of rewriting, but not much, and it wasn't very complicated, okay? If you think back to when we did power rule with differentiation, we sometimes had to do some division, sometimes had to do some multiplication before we could actually take the derivative. The same thing's going to be true when we have antiderivatives, okay? For example, please write this down. Okay, we cannot take the antiderivative right now. What do we need to do in order to be able to take the antiderivative? How can we rewrite this so that we can?
Separate the terms.
Okay, separate the terms. And also consider that we're dividing by x squared. Okay, so what is x cubed over x squared? Negative 5x squared over x squared. Negative 5. Square root of x over x squared would give us x to what power? And then minus, I would write this as 7x to the negative second. So now we can do the power rule for each individual term. So now, antiderivative of x. Josie, what is it?
It's kx plus c, right?
The antiderivative of k is the qx plus c. So we have x to the first. If we take the antiderivative, what do we have to do with our power?
Oh, so it'd be 1/2 x.
There you go. Okay. Okay. Q, -5. What's that antiderivative?
0.
0 would be its derivative. -5x would be its antiderivative. Good. Let's see. Isaac Warner, x to the -3/2. Like that. -2. Okay, increase the power, so x to the -1/2 multiplied by its reciprocal, -2. Okay, and last but not least, Jake, what about -7x to the -2nd?
Plus 7x -1.
Plus 7x to the -1. So we increase the power, multiply by its reciprocal, which is just -1. And then what do we need at the end? Plus c. Okay? You can leave your answer like this. You can rewrite it so you have, so you don't have negative powers. It doesn't matter, but I'm fine with this. If you do not have a simple x to a power, rewrite it so you do have x to a power, and then you can use the power rule for your antiderivative. Go and write this down. Okay. Cole, are you saying the 5 is with the x taken to the 1/2? Is that what you were discussing?
Yeah.
Okay. So when we do the power rule here, we can take 5x, and what was our new power? If the power is 1/2, then the power is going to become 3/2. We then have to multiply by the reciprocal. But then if we think about taking this derivative, okay, if we take this derivative, we have to do the chain rule. Do you agree? And when we take the derivative, our chain rule would be we have to multiply by 5 after we take the derivative. So when we take the antiderivative, we have to keep that in mind. And since we have a coefficient with that x, we have to think about that chain rule coming into play. Okay. So what we really have is 2/15 5x to the 3/2 plus c. Now, how do we know if we have the right answer or not? Okay, if we take the derivative, we should get back to what we started with. Okay? And if we take the derivative, that would happen. Okay, you want to check? We take the derivative, we would have 2/15 times power rule, 3/2 times 5x to subtract the power times chain rule of 5. So the 2's cancel out, 3/15 times 5 cancels out, and we're left with 5x to the 1/2. We're right. Let's talk about some trigonometric antiderivatives. You experimented a little bit with sine and cosine on that activity sheet on Friday. So let's go ahead and officially define all of our trigonometric antiderivatives. Okay. Okay, first we'll start with the antiderivative of cosine. I would just write what I have in red. What I have in black is for us to consider, so we can go the other way. Okay? So the antiderivative of cosine. If the derivative of sine is cosine, then the antiderivative of cosine would be sine of x. Next, we'll talk about the antiderivative of sine. If the derivative of cosine is negative sine, you remember this is something you thought about on Friday, the antiderivative of sine was negative cosine. All right, so our negative rule flip-flops because we're going backwards for antiderivatives. Okay, so now you have to keep straight the negatives and positives for derivatives and antiderivatives. Okay. All right, now the derivative of tangent is secant squared. So if you have the antiderivative of secant squared, we know that is going to be tangent. With your knowledge right now, we can't find the antiderivative of just secant. Okay? You'll be able to later in your calculus career, but not right now. Okay, we know the derivative of secant is secant tangent, and so the antiderivative of secant x tangent x is secant x. Similar rule, the derivative of cosecant is negative cosecant cotangent. So the antiderivative of cosecant cotangent is negative cosecant. And last but not least, we know that the derivative of cotangent is negative cosecant squared. So the antiderivative of cosecant squared is negative cotangent x plus c. Alright, we're going to practice some of these basic ones, and then I'll show you an example of a problem where we could have to rewrite something. Where do you have it? Yeah. we have the integral of cosine of 7x dx. Remember, that's how we would read that mathematical expression. Larry, what's the antiderivative of cosine?
Sine.
Sine. Is it positive or negative?
Positive.
Positive. Okay. So the antiderivative of cosine is sine. The angle does have to stay the same. So we have sine of 7x. Is that it though?
No, yeah. In the inside, the one side.
Okay, we have to account for, if we were to take the derivative, we would have to multiply by a 7 to get back. So we're going to have to multiply by a 1/7 to ensure that when we take the derivative of our answer, we get back to what's inside our integral. Go ahead and write this one down. Okay, so I have a couple of rules mixed in here. Okay, we are taking the antiderivative with respect to theta. So if we just have theta right here, Austin, what's going to be the antiderivative of theta? Or we are taking the
We're taking the derivative.
Mhm.
So that would just be, wouldn't that be 1/2 theta squared?
Good. So that theta is kind of like an x. Okay, so we have that power rule going. So we increase the power, multiply by its reciprocal. Okay. Minus. You can either think of that as a negative sine of theta or minus sine of theta. Okay, so we're subtracting. Abram, what's the antiderivative of sine theta?
Negative cosine.
Okay, so if the antiderivative of sine is a negative cosine and we're subtracting, this is going to become minus negative cosine. I didn't leave myself enough room, did I? All right, and then cosecant squared. Okay. Michael, what's the antiderivative of cosecant squared?
Negative cotangent.
Negative cotangent? Okay, so we are subtracting a negative cotangent of 3 theta, but since that 3 is inside with the theta, what do we need to multiply cotangent by? 1/3. Very good. What's nice about antiderivatives is it helps you practice your derivatives. Okay, because you're just thinking backwards about it. All right, last trig problem. Okay, can we take the antiderivative right now? We cannot. We cannot take an antiderivative of a fraction. We have to have single terms right now. Okay? So we are going to have to rewrite this until it is something that we can take the antiderivative of. Okay? So let's play around similar to what we did with that polynomial one. What is cosine cubed over cosine squared? Just cosine. And then sine over cosine squared.
Separate sine over cosine tangent, and then we'll have a 1 over sine, and that's secant. So
Okay, very good. If we're considering sine over cosine squared, we have sine over cosine, and then we have a cosine left over. So what we have is secant tangent. So now we have the antiderivative of cosine, which is sine, and the antiderivative of secant tangent, which is secant. Okay. When we did derivatives, what was the easiest derivative ever?
Constant.
The next easiest. There's one easier than
X.
e to the x. That's what I'm going for here. Okay. What was the derivative of e to the x? E to the x. So the antiderivative of e to the x is e to the x plus c. All right, so first question. Okay, this is what I call like the copy paste rule. The antiderivative of e to the x is copy paste e to the x and plus c. So your antiderivative of e to the negative 2x is e to the negative 2x plus c. However, okay, since there's that negative 2, and if we were to take the derivative, we would multiply by that negative 2. So when we take the antiderivative, we're going to multiply by the negative 1/2. That way, when we take the derivative, we get back to a positive e to the negative 2x. Does that reverse chain rule make sense? Okay. Now, we can really only do this if we have something linear inside. If that was e to the x squared, it would not work. But as long as we have something linear inside of our function, we can do that. Let's see about this one. Can we take the antiderivative right now since it is a fraction? We cannot. We have to have individual terms, okay? So we have to separate this out like we've done, I think, a couple of times already today. Okay? So how do we rewrite 5 over e to the 2x? 5 times e to the negative 2x. We can do that up. Minus, if we have e to the x and we're dividing by e to the positive 2x. What do we do when we have the same base but we're dividing? We subtract. So if we're subtracting exponents, what is x minus 2x? Negative x. So this is how we can rewrite our integral. Okay, so we have 5 times the antiderivative of e to the negative 2x. We already decided was e to the negative 2x times negative 1/2 minus the antiderivative of e to the negative x would be e to the negative x. And then what would we have to do there? We would have to multiply by that negative inside. So it would become plus e to the negative x. Okay, so our final answer, I would want to see negative 5/2 e to the negative 2x plus e to the negative x plus c. Okay, last rule. Are you ready? If we have 1 over x, and we rewrite that as x to the negative first, can we use the power rule on that? What would the talk about it with your cause? Why is the power rule not okay in this instance? And can you think of what the antiderivative would be?
You gotta multiply that by
Okay, top 5. Why is the power rule not going to work out?
It's like you get 0 or something.
You get x to the 0, right? And then trying to multiply. Not going to work. Okay? What would the antiderivative be of 1 over x? Natural log. The derivative of the natural log is 1 over x. So the antiderivative of 1 over x is the natural log. However, we do need to put absolute values inside of the logarithm because we have to account for the fact that we can't have negatives inside of our logarithm. And when we do antiderivatives, it doesn't always account for that, so we have to put them in there. Okay, so we're going to do 1, 2, 3 more examples. We're done. Okay, are you ready? First example, integral of 7 over x dx. This is an instance where I would not mind rewriting it as bring the 7 outside, and so then you can see we have 1 over x dx. You see that? Okay. And then we can consider, okay, we have 7 times the integral of 1 over x dx, we decided was the natural log of the absolute value of x plus c. Second example, the integral of 1 over x minus 5 dx. As long as we have a linear denominator, we can use the natural log rule. Okay? We have 1 over a linear denominator, so this antiderivative is going to be the natural log of the absolute value of x minus 5 plus c. As long as your denominator is linear, you can use this rule. Go. Last example. Go down. Can we take the antiderivative right now?
No, it's not linear.
Well, it's not necessarily that it's not linear, it's that we have a fraction. We can't take the antiderivative of a fraction. We need individual terms. So x over x squared, we can rewrite as 1 over x. And then we can add 2 over x squared. Some of you are getting to the point where 2 over x squared you rewrite in your head and then take the derivative or antiderivative depending on what we're doing. There's nothing wrong with rewriting it one more time. I like seeing this as 2x to the negative second. Okay, so we can think about power rule. Okay, I didn't rewrite this one because what is its antiderivative? Natural log. We can't use the power rule on that one. So we have the natural log of the absolute value of x plus, Logan, what's the antiderivative of 2x to the negative second?
Negative 2x to the negative.
That is 3. Okay, so here's what I want. I decided we're going to wait for particular solutions until after break. So you're going to have a worksheet and a few book problems. You can't just do the worksheet and you can't just do the book problem. So what I would do is complete the worksheet, it's pretty short, and then do the book work on the back. Okay? When I hand this to you, I want you to cross out the top 6 through 10. So in the e to the x group, I want you to cross out 6 through 10. So you're just going to look at it.
No, I was gonna flip side. Another one. Oh, it's another riddle.
It is another riddle. Now, the top one you're not going to really get because I'm making you cross out 6 through 10 on the e to the x one, but the log cabin one,